This is a production of the Chemical Education Material Study.
Electricity is a moving force in our lives. One of the great advantages of electricity is the ease with which it can be stored in small, even tiny containers called electrochemical cells. Each cell contains only 2 electrodes and a chemical electrolyte. When 2 or more cells are used, they are called a battery. Car batteries contain 3 to 6 cells, that is 6 or 12 electrodes. Electrochemical cells provide current and voltage, which can accomplish a great variety of tasks. What goes on inside an electrochemical cell?
In your laboratory experiments, you may have constructed an electric cell similar to this one. 2 beakers containing metal sheets and ionic solutions are connected by this U-tube filled with an electrolyte, aqueous sodium nitrate. We complete the external circuit between the copper electrode in one beaker and the zinc electrode in the other beaker. An electric potential is recorded as voltage. Removing the U-tube breaks the circuit. The 0 reading on the voltmeter shows the cell is no longer operating. Only a completed circuit, internally within the cell, as well as externally through the wire, allows an electric cell to operate.
Let's examine another electrochemical cell arranged for easy observation. We chose colorless clear electrolytes so you can see changes which occur. We immerse the 2 electrodes. One electrode is copper. It is immersed in an aqueous solution of sodium nitrate. The second electrode is silver in an aqueous solution of silver sulfate. Completing the cell is a porous barrier. It prevents mixing, but like the U-tube in the previous cell, permits ions to penetrate. But have we really constructed an electrochemical cell? Does it generate an electric potential? It does. In fact, almost any pair of electrodes in any electrolytes will generate a potential. But what chemical reactions led to a potential in this cell?
We have copper and silver electrodes immersed in electrolytes. The solutions are kept from mixing by the porous barrier. On the left, there are positive sodium ions and negative nitrate ions. And on the right, positive silver ions and negative sulfate ions. All the ions are in random thermal motion. The barrier prevents the mixing of the 2 solutions. Although we can't see them, reactions are taking place at each electrode. Look at what happens when copper is placed into the solution. Initially, copper atoms, nitrate ions, and sodium ions are present. But at the surface, copper atoms can give up 2 electrons, be oxidized, and enter the surrounding solution as copper ions. The freed electrons give the electrode a net negative charge. Some of the copper ions, in turn, can strike the copper, gain 2 electrons, and be reduced to solid copper. At equilibrium, a net negative charge has accumulated on the copper electrode. As a result, only a minute amount of aqueous copper ions are present at equilibrium. The equilibrium half reaction involves solid copper, aqueous copper ions, and electrons.
Now let's look at the similar equilibrium reaction at the silver electrode. Here the positive silver ions of the silver sulfate solution strike the silver electrode and adhere. Each reacting silver ion takes up an electron to become silver metal. Simultaneously, a different silver atom can lose an electron to form a silver ion. We can express this equilibrium by this half equation. Silver ions, aqueous, plus electrons in equilibrium with silver solid. Again, only a minute amount of reaction occurs because of the accumulated charge at the electrode. Thus, before the circuit is closed, equilibrium exists at each electrode. Different amounts of charge have accumulated at each electrode since the metals as well as the electrolytes are different. The copper electrode has become more negative than the silver. What will happen when we connect the electrodes directly? Let's return to our cell and find out.
We close the circuit by connecting the two electrodes with a conducting wire. Time-lapse photography compresses 12 hours into a few seconds. The copper side of the cell gradually turns blue. Simultaneously, crystals grow on the silver electrode. Now, watch the copper electrode process once more. You might guess that the blue color appearing around the copper electrode comes from aqueous copper ions. Separate analysis confirms this. Oxidation of copper atoms to copper ions roughens and darkens the surface. The electrode at which oxidation occurs is called the anode. The oxidation half reaction is copper, solid, gives copper ion, aqueous, plus 2 electrons. Now look at how the silver electrode changes. After the external wire is connected, we see, still in time-lapse photography, shiny metallic needles growing from the surface of the electrode. Analysis shows that these needles are metallic silver and that the electrode is gaining mass. Reduction of silver ion to silver metal is occurring. The electrode at which reduction occurs is called the cathode. The reduction half reaction is silver ion, aqueous, plus 1 electron gives silver solid. Here is the complete cell. Oxidation of copper at the anode frees electrons which flow through the external circuit to the cathode, where silver ions accept electrons and are reduced to metallic silver. The positive copper ions are now distributed throughout the left compartment. But have any copper ions passed through the barrier into the other compartment?
Let's check the barrier material first. We place some aqueous copper sulfate on a piece of the barrier. Penetration is slow, but in a little while diffusion occurs. The barrier is porous. A sensitive test for copper ions is the blue color they form with aqueous ammonia. When the solution from the cathode compartment is also tested, a faint blue color forms. Even though the barrier was designed to minimize mixing, some positive copper ions have moved through the barrier from the anode toward the cathode. Have positive silver ions moved through the porous barrier in the opposite direction? When the solution from the cathode side of the cell is added to aqueous sodium chloride, a white precipitate of silver chloride forms, as expected. Using this same test, we'll check for silver ions on the left side of the barrier. No precipitate forms. Within the accuracy of this test, no positive silver ions have moved toward the anode. Silver ions have remained in the cathode compartment. The barrier has prevented general mixing. We have now seen that the copper ions move through the barrier to the right half of the cell, and that the silver ions do not move through the barrier to the left. But what about the negative sulfate ions, which were originally in the right half of the cell? Do they move across the barrier? Let's check the motion of the negative ions. If we mix sulfate ions, such as those in the cathode half of the cell, with aqueous barium ions, we obtain a white precipitate, barium sulfate. Now we'll test for sulfate ions in the other half of the cell. A precipitate forms, indicating that negative sulfate ions did move toward the anode from the cathode compartment. So you can see that copper and silver ions tend to move toward the cathode. So do all positive ions, while negative ions, such as sulfate, tend to move toward the anode. We have also observed that copper is oxidized to copper ions around the anode, and silver ions are reduced to metallic silver at the cathode. How can we account for all these observations?
You may remember that prior to the closing of the circuit, there was a difference in potential between the anode and the cathode. Closing the circuit provides a path for the electrons to flow from the copper anode to the silver cathode. At the copper electrode, copper ions require electrons if they are to form atoms of copper metal. This reaction becomes less frequent as electrons flow away in the external circuit and fewer electrons are available in the metal. However, copper atoms continue to give up electrons. There is a net formation of copper ions, which then migrate away from the anode. So closing the circuit upsets the original equilibrium. Simultaneously, at the silver cathode, the inflowing electrons make the reduction of silver ions more likely. The electrons supplied from the copper anode make it more likely that silver ions will be reduced to silver metal. The previous tendency of the silver metal to lose electrons back to the electrode is now overbalanced by the tendency of the ions to acquire the inflowing electrons. Equilibrium no longer exists. There is a net reduction of the positive ions to silver metal. The total effect produces movement of positive ions through the solution toward the cathode, movement of negative ions toward the anode, and a flow of electrons through the wire from the anode to the cathode. This is true in every electric cell. After the cell has operated for a long time, the potential drops to zero. The cell is dead. There is no longer any net tendency for electrons to move between the electrodes. Why is this?
Initially, before the circuit was closed, the electrodes were immersed in sodium nitrate and silver sulfate, respectively. The silver sulfate solution provided a large number of silver ions. Some of these ions react at the metal surface, but equilibrium is maintained. Only a very small number of copper ions are provided by the equilibrium reaction at the copper electrode. When the circuit is closed, equilibrium is upset. There is a net oxidation of copper and reduction of silver. The positive ions undergo a net motion toward the cathode. As the concentration of copper ions increases, the concentration of silver ions decreases. At some small concentration of silver and some large concentration of copper, no further net reaction will occur. A new equilibrium exists. With this new equilibrium, there is no net tendency for electrons to flow from one electrode to another. That is why the potential of the cell is zero. Thus, we see that as the ionic concentrations change, the voltage drops toward zero.
Not all cells involve simple oxidation and reduction of solid electrodes. This cell uses gaseous hydrogen at one of the electrodes. This cell has a potential of about 1 volt. Again, one electrode is silver in a solution of silver sulfate, but the second electrode is the relatively inert metal platinum, over which hydrogen gas is bubbled. The rough black platinum surface is used to bring electrons into electrical contact with the gas and the solution. The solution is dilute sodium hydroxide. To study the cell reaction, we will use bromethymol blue indicator. Let's check the indicator's color as acidity varies. It is yellow in acidic solutions. It changes through a set of intermediate colors in neutral aqueous solutions and is blue in basic solutions. We add the indicator around the hydrogen electrode. The blue color indicates that the solution is basic. Now we disconnect the voltmeter and complete the circuit with conducting wire. Watch the indicator around the hydrogen electrode as the cell operates. The solution, which was basic before the circuit was closed, is now acidic, showing that as the cell operates, hydrogen ions are forming. Here are the standard tubes to confirm this. The equation for the half reaction at the platinum electrode must be hydrogen gas gives 2 electrons plus 2 hydrogen ions, aqueous. At the silver electrode, the half reaction is silver ions, aqueous, plus 1 electron gives silver solid. Now we'll disconnect the cell and measure the potential again. We would expect the operation of the cell to have decreased the cell potential from its earlier value of about 1 volt. Yes, the present value is only 0.8 of a volt. Normal operation lowers the cell potential. What would happen if we now further decrease the concentration of silver ions? Addition of an aqueous sulfide solution will do the trick by converting much of the aqueous silver ion to insoluble Ag2S. Watch the voltmeter as we add sulfide ions. The cell potential shifts as the silver ion concentration decreases. The needle moves to the opposite side of the scale 0. This indicates that the flow of electrons in the cell has actually reversed. The hydrogen electrode is now the cathode. Let's check this experimentally by observing the bromethymol blue once more. We disconnect the voltmeter and connect the electrodes directly to each other. Now watch the indicator color. The change from yellow to blue indicates the hydrogen ion concentration is decreasing. Hydrogen gas is now being formed by the reduction of hydrogen ions. The electron flow has reversed. This electrode is now the cathode. The solution becomes basic, as the comparison tubes remind us. In the initial setup, hydrogen gas reduced silver ions present in large concentrations to produce hydrogen ions and silver metal. But when the concentration of silver ions was decreased by addition of sulfide ions, the net reaction reversed. Metallic silver then reduced hydrogen ions to produce silver ions and hydrogen gas. So the potential of a cell and even the direction of current flow are highly sensitive to the concentrations of the reactants. But at constant concentrations, the potential is constant.
Working at standard concentration allows us to measure voltages known as E0 values. For example, an E0 potential of 0 volts is arbitrarily assigned this half reaction, producing H2 gas at 1 atmosphere pressure from 1 molar aqueous hydrogen ion. Each E0 value serves as a comparison with potentials of standard concentrations of other substances at standard temperatures. These E0 values may be combined to predict unknown potentials, and hence the tendency of new electrochemical reactions to occur. Positive E values for any net reaction indicate the reaction is spontaneous. Further studies such as ours would show that all electrochemical cells operate in a similar fashion. The positive ions move toward the cathode, the negative ions toward the anode. Simultaneously, there is an external flow of electrons from the anode to the cathode. There is oxidation at the anode, reduction at the cathode inside every electrochemical cell.
The flowing electrons driven by the cell half reactions provide those power sources without which your life would be quite changed. Perhaps you would like to discuss what is happening in this experiment.